Welcome back to Behind the Bumpers. Today I'm here with Team 2046 Bare Metal at the Pacific Northwest District Championship event. They're having a great season with 2 banners and an impact already under their belt. So we're going to go into their incredible robot on this episode of Behind the Bumpers.
This video on fun is brought to you by viewers like you and also in partnership with the following.
Build your alliance with so many other FRC alumni who go to Kettering University. Every student at Kettering experiences their cutting-edge co-op programs that seamlessly blend the professional and academic worlds. Kettering co-ops are a fully immersive working experience at the leading edge of industry. Head on over to kettering.edu/FRC to learn more about their incredible programs and to get more information. Earn up to a $5,000 sponsorship for your team or $2,000 individual prize when you provide a video submission to the Altair Global Student Contest at altair.com/contest. You can build better robots faster with Altair tools and provide multiple video submissions for the contest. Download Altair tools for free. Scan the QR code or go to altair.com/contest for further details.
So for this season, we wanted to emphasize creating an effective architecture that can both maximize our scoring ability in the game. So from the start of the season, we kind of came up with 2 different architectures, one with a perpendicular elevator to our ground intake, as well as one parallel to our ground intake. And in our analysis of the strategy for this game, we thought it was very pertinent for us to be able to pick up from the ground, being that defense at the human player stations could be heavy, especially with the limitation of only having 1 defender on each side. So we wanted to be able to not be affected by good defense. So just to walk through our mechanical mechanisms, we have our ground intake, which has a flexible front roller on dead axle stubs, both to prevent breakages on our rollers for our intake, as well as to be able to collect coral from any position anywhere on the field. So that serializes through a star wheel indexer system, which orients the coral into a parallel position for our end effector. The coral feeds through on an angled ramp, which allows us to give clearance for our end effector, as well as being able to essentially add controllability for our sensors and stuff like that. Some of the main things that we wanted to emphasize for this season as well is weight reduction. With the reduced weight limit for this year, we wanted to make sure that we are preemptively going through and making sure that we actually have enough weight to implement all of the elements of our robot. So, for example, we wanted to, later in the season, we actually went and drilled out the ID of our axles in order to reduce the amount of weight that we get for each axle. In general, being able to maximize our weight reduction for using thinner material or thinner aluminum or heavily weight reduced materials, using churro stock, for example, as well as churro stock for axles, which is another main thing for our weight reduction. But just in general, emphasizing the amount of weight reduction that we have on our robot. Furthermore, we can go into our climber. Our climber is actuated with the 2 Kraken X60 gearbox, which has actuating solenoids on each side to allow us to ratchet one way for going up and back down so we don't fall during the match. This is driven by 35P chain up into our active grabber. Our grabber essentially spins these compliant wheels into these one-way latches made out of half-inch polycarbonate, which allows us to essentially latch onto the cage pretty quickly. In addition to that, we also have centering for our deep cage, which allows the driver to have a greater margin of error away from the cage when we're approaching the deep cages. So just to move on from our climber, we have our arm, or our arm and elevator system, our main piece for our robot. So for this year, we went with a 2-stage elevator with a 22-inch long arm, because we found that through previous years' experience with 2023, a huge emphasis on having multiple modes of motion, allowing us to get to our set position for our scoring much quicker, being a main emphasis in our strategy for this year. So just to go to our elevator real quick, we have, on top of having a 2-stage elevator, we actually have an externally rigged continuous elevator, which both to emphasize the fact that we wanted to be able to service our elevator easily, as well as be able to see the tension of our belts much more easily, with the nature of belts stretching over time and not having to worry about it over the season. Some of the main things that we have to go about with tensioning the belt is we have a rotational tensioners on our carriage, which allows us to use ratchet plates to essentially ratchet one way and increase the tension of our belt rigging. And in addition to that, the reason why we went with a 2-stage elevator is to, again, reduce the amount of effective mass that we're moving. Inherently, moving less mass, therefore a lot more acceleration in our system. So we actually have a 4-to-1 gearbox that is driven at the bottom of our elevator, especially with an emphasis for us being reducing the height of our CG, just across the robot in general. So kind of to move on to our arm, we have a coaxial arm, which allows us to drive our end effector separately without having a motor at the end of our arm to, again, reduce the amount of inertia that that we have on our arm. So yeah, with increasing speed, we also have a lot of packaging or dense packaging to reduce the width of our elevator. And a lot of that factors into the fact that we have a coaxial arm. So that allows us to have one drive kraken for the rotation of our arm, as well as a drive kraken for our end effector. So essentially, we can demo this real quick if you hold the carriage. We're able to rotate our arm and translate it anywhere, while also being able to drive power for the center of our billet post for our arm. And this is all driven onto our 3D printed hub, which is made out of onyx, Markforged onyx with Kevlar inlay to increase the rigidity of our arm, as well as to be able to make it as light as possible. And on top of making that as light as possible, we actually have a carbon fiber tube adhered with hot glue onto this 3D print, which allows us to essentially, again, reduce the amount of mass, but also increase our reliability. So part of that reliability formula, I suppose you could say, is with using hot glue, we're able to easily replace this carbon fiber assembly up after the joint. So in the case that we have a breakage, say on the tube itself and/or on the shoulder piece, we're able to quickly replace it by essentially just heating up the hot glue, which adheres it, and allowing us to pull it off, rather than having to use epoxy, which is a more permanent solution, causing us to have to basically throw away a carbon fiber tube every time we go and break our arm. And just to add furthermore onto that, we can move on to our end effector. Our end effector is also retained through a 3D print that's at the end of our arm, which is using the same Markforged onyx with a Kevlar inlay to, again, just increase the amount of rigidity and strength in our arm. And essentially, with the internal timing belt through our coaxial arm drive, we're able to essentially translate it from this axis up and through into our end effector. With our end effector, we actually grab externally onto the coral, which allows us to both pick algae off the reef, as well as be able to score any position on the reef opposite from our intake. So we can see here, grabs onto the outside of our coral, and it's able to score both onto L1 through L4, but as well as be able to pass through for all of those scoring positions. So one of the main challenges that we actually had earlier mechanically in this season, because we used to grab onto the internal side of our coral, is being able to score onto the L1 more effectively. And part of the solution for this end effector is being able to score onto L1. So we can actually, in our downward stow position for our arm, we're able to only pivot around 30 degrees upward in order to score into the L1 trough, which just increases our cycles and being able to collect from one side and score on the other. And also another part of our equation for this year is being able to score barge, as well as collect algae off the reef. And we found that with our previous end effector with the internal grabber, that we wouldn't really be able to add an additional tusk to hold onto algae as easily. So we needed to figure out an alternative solution, and we came to this outer grabber as that solution.
Yeah, so a big thing we wanted to do this year was cut part count so that we could have a lighter weight robot and we could still do complex stuff. So the way we achieve that is with billet. So the most complex part on the robot is going to be our center post. It goes in right here, hidden by the carbon fiber. This allows us to have one piece that lets the arm rotate on, as well as having a hole straight to the middle for coaxial power. The way we machine this is we do op 1, and then to hold it for op 2, we machine custom aluminum jaws right here, and the part fits in and locates inside of the jaw, and then we can machine the second op. This is allowing us to machine it quickly. We made a lot of these for like spares and that kind of stuff. I'm just really loading it easily. Another big piece of this was the external ring that goes around. So this is a slip fit inside of the print, and then has bearings that also slip fit into it, and then slip onto this surface. So this allows one for the whole arm to be taken off with just a ring clip right here, and allows for pretty good concentricity inside the arm. So moving on to some of the other parts, we wanted to have posts, an externally rigged elevator, and we wanted to be pretty simple. So we went with one piece post, so it's tapped on the end, and then there's a little ring clip groove for a small ring clip, and those just live right here. So this was allowing us to, again, cut weight, so you don't have like washers, or for example, maybe like an axle glued into a plate. So if I can talk about the carriage for a little bit. You want to hold it? Yeah. So on each side of the carriage, we have 4 op plates with custom bearing blocks machined into them. So this allows us to be very weight efficient versus like using like SDS bearing block. This is the weight of 1, and it serves 2 and a plate. And it also has like tapped holes on the sides of it, so we can hold stuff together. Another big piece we have on here is gonna be like these little standouts right here. This makes the elevator like much more rigid and stronger right here. And it's just simple assembly. And if you want to flip it around, we're going to talk about this piece right here. This is a last minute change to stop this axle from cantilevering, and it's just one piece slips in, and there's a little feature inside of there that fits onto this, and it's all machined. So another thing we really want to do cut weight is we want to use X44s on our steering motors, but we didn't want to use an adapter plate because it's more heavier. So we went with the approach of completely machining the SDS plate in-house with like some weight reduction changes so that we can hold the X44. So the final thing I'm going to talk about is our fabrication priority sheet. And with all these parts on the robot, we want to be able to track them efficiently. So our system engineers will go and put all of the information onto the sheet, and then fabrication will look at what needs to be made, and we'll go through and make that, and then check off like where the part is, for example, like being machined or like being programmed. So yeah, yep.
Yeah, as Colton was saying, the fabrication priority sheet is one of the things that really allows us to improve the efficiency of our team. We actually have a subset of members on our team who are systems engineers, and that is their whole purpose, is just to make our team run more efficiently. So we have multiple systems like the fabrication priority sheet, or we have an electronics quality control sheet. We go through multiple design reviews that the systems engineers go and look over, and make sure every question is getting asked, every possible issue with the robot is being addressed. Something else we did this year that was really interesting, in my opinion, is we did a lot of different types of block cab, and that goes back to the architecture. We went through and we looked at multiple different architectures and took a really systematic approach to choosing our architecture, and making sure we weren't gonna just, pull in on one design that was maybe not the best. Another thing we did this year was just really try to implement or integrate our assembly and our electronics team. That's something we struggled with previously. It's just having slow assembly and slow electronics, and kind of merging them together really helped with improving the overall process, allowing us to get a robot out much faster.
I can talk more about the electronics. So one of the most important things for us to do is to have electronics done quickly and to make sure there's no electrical failures during the season. So some of the things we do to get that done is, as you said, we alternate the assembly and electronics right next to each other. So when the chassis is done being assembled, the electricians went in and wired it, and then once elevators put on, then we wired that. So that process helped us speed it up a lot. And then a lot of what we do for reliability is we solder all of our wires, so we try and minimize the amount of failure points on a robot, and make it so that it's just less likely to break during a match. And one of the ways that we help to both speed up the process and ensure nothing gets broken is we laid out our wires and CAD beforehand. So if you come look here. So this is a sketch in Inventor where every single wire was laid out and color-coded, where it would go, what motor it's going to, and where we wanted it routed. And so that allowed us to add zip tie holes in the correct places and to ensure everything's strain relief so it doesn't get broken. Okay, we can come on over, see on the underside of the robot. So one of the other things we wanted to try this year was reverse mounted electronics. So we have our PDP2, our Pigeon IMU, and then our 2 mini power modules reverse mounted on the robot. And so we did this so that we're not reaching into our robot when we have to fix things. We can just tip it up and work on it really easily. And then also so that we don't have things falling into it, so it can be completely protected by this polycarb cover. And so you can see here where some of the zip tie holes went and how we routed the wires and how that ended up. And in order to keep the wires protected and make it a lot cleaner and keep them clean, we routed a bunch of wires to this tube right here, our cross chassis tube. And part of that routing was we integrated grommet holes. You can see those right there, in order to keep them from getting like caught on the edges and keep them from getting, and the rubber coating will keep it from like biting into the insulation. And speaking of the PDP2, last year one of our biggest electrical issues was when we would brown out at the end of matches after like pushing matches and stuff like that. So we tried to decrease the amount of voltage drop in our system so that we're not browning out as much during matches. So there are lots of elements to that. One of the main ones was using the new PDP2, which has, I believe, a third of the voltage drop of the PDH, which is what we used last year. And then we also use the first 4 ports on the PDP, which have decreased resistance for our drive motors. We use 10 gauge wire just to get that little bit of decreased resistance. And then we also try and like weight reduce a decent bit on so for non-essential things such as the like collector spinning motors and the steer, we use X44, so we're not don't have as much weight and aren't drawing as much current. See that right there? You can tip up now. So a couple other things we integrated. So in our indexer, in order to sense when we index a piece, we added a beam break sensor, a retroreflective beam break sensor, which should slide up. I'm gonna turn on the robot real quick. Which shoots light up, bounces it off the reflective tape, and then bounces back down and senses it. And so you can see the orange light turn off whenever you put your hand through it. And one of the ways we had to integrate this is that that component needs a pull-up resistor and it needs to be read by the RIO, which is on 5 volts. So we had to have a pull-up resistor and a voltage divider. If you can come over and look at the book. So this was actually a custom PCB designed by me. That was a project that we worked on that had, in order to keep it, keep all the resistors organized so there's nothing bridging, and to keep the wires strain relieved. Okay, and the next thing we'll talk about is we had our vision. So we run a Orange Pi and 2 Arducams running photon vision, and a Limelight we use for coral detection. And we can pass it off to our programmers to talk more about our vision and programming.
Yeah, so as Asher said, starting off with vision and auto, I guess, we have 2 Arducams facing the reef as we're scoring out the side. This helps us auto line on the reef. We have 2 because, I mean, either side of the pole, you need to be able to see the April tag the whole time. And then on this side for the Limelight, we use this heavily with our ground intake. It is facing towards the ground. We use that AI detection for those coral during those autos just to ensure that we collect those pieces 100% of the time. Another thing that was like just a super hard programming challenge was this 2-DOF system here. This arm is like really big and has a lot of collisions. So to prevent this, we developed our own like trajectory command class that takes in a starting point and an end point, and then if we need to, different waypoints along the way. This just allows us to transfer in between all of our states independently and without like hitting any collision points. We found out that how fast we're moving this arm, we needed to develop a full like inverse dynamics class that basically takes all of our velocities and calculates feed forward voltages just to ensure that the arm and the elevator are getting to the right locations at the right time. And yeah, there's just a lot of tuning that went into that. We also implemented recently a auto collection system using AI detection in teleop. This just is a super easy way for the driver to collect consistently as well. So there's not that much driving going into the process, and we're just a lot more efficient in our teleop control. And yeah.
All right, thank you, Bare Metal. This is an awesome robot. You're having a great season. I can't wait to see how it goes from here. Good luck with the rest of your competition.
Thanks for watching. Don't forget to like, subscribe, and click the bell to stay up to date on future fun videos. Earn up to a $5,000 sponsorship for your team or a $2,000 individual prize when you provide a video submission to the Altair Global Student Contest at altair.com/contest. You can build better robots faster with Altair tools and provide multiple video submissions for the contest. Download Altair tools for free, scan the QR code, or go to altair.com/contest for further details. Build your alliance with so many other FRC alumni who go to Kettering University. Every student at Kettering experiences their cutting-edge co-op programs that seamlessly blend the professional and academic worlds. Kettering co-ops are a fully immersive working experience at the leading edge of industry. Head on over to kettering.edu/FRC to learn more about their incredible programs and to get more information.